specifically in terms of graph neural networks, the way we think about the problem and sort of decomposing it is, first of all, what kind of models are you attempting to train? Is it driven by attempting to train the entire graph at once, so which we might call full graph training or full batch training, or are you trying to do it using mini batches, which is the more traditional sort of neural network, in the vision space or the NLP space that you might use, where you use mini batches to train the graph neural network, right? So that is one sort of challenge that we have to address, and we have to ask ourselves for the given application. For example, what Venkatesh said, if you want to do this anti-money laundering kind of application, should you look at the entire graph as a complete entity, or do you do them as mini batches? So that's one problem to solve. Having done that, next you want to ask yourself from a system design perspective, how do you partition these graphs? So there are different ways of doing it. There are different algorithms. For example, there is the meta system, which will partition the graph along the edges. So there's edge cut, and so you now have graphs that are partitioned into, across different instances, CPU sockets or GPUs or whatever, and now you have to have interaction between those partitions. Another method is done by what is called this Libra library, which splits the graphs along the vertices. So you have vertex cut. And then there's another school of thought, which is, why even partition anything? Just partition the model. Forget about the graph. Just leave the graph as it is. So this is a set of systems, challenges that have to be solved. Third, once you look at these two aspects, once you've partitioned the graph, now if you want traditional graph neural network primitives, which primarily are aggregation of some sort, and update, right? So these are the two key things that you do. You gather features, feature vectors, you perform some sort of aggregation algorithm, and then you perform an update, and then you scatter back if required. So now, how do you do this when these graphs have been partitioned across remote systems? So now you have to have communications, and potentially you could have a situation where communication becomes bottleneck, and you don't want to have that happen. So now you design clever communication avoidance or communication reduction sort of algorithms to ensure that your communications don't become a bottleneck. And finally, last but not the least, once you've actually figured out all of these things, how do you actually get the compute to run efficiently on the underlying machine, whether it's a CPU socket or a GPU card or whatever it is. Again, to do both of these aggregation operations efficiently, as well as the update operations extremely efficiently. So these are the sort of high level systems challenges that we look at from a top to bottom perspective when we do these analysis and optimizations.